Okay, guys, I think we're gonna start. So, welcome on our 14th event of Cracow Robotics and AI Club. It's such a thrill to see so many of you in here. And let's start with our sponsors. So, first of all, shout out to Hubraum, for hosting us in here, for giving us all of this space. They are a startup incubator, and if you're interested, like, reach them out if you have great startup idea. Also, our shout out to Huzarion for providing us with beer, and to Weekly Robotics for helping us to market the event. For today's agenda, we will start. Actually, we had to flip the order, so just note that it's different compared to LinkedIn. We will start with Katarzyna, and she will tell us more, she will provide us with insights on how to mix different inputs of localization, how to mix and match them on a robot in real life. Later, we'll have a short networking break. Afterwards, Marcin will present us with his project on a, how to put it? Well, mechatronic mannequin is a great way. You will see. Great project, but basically mannequin for clothes that can scale to the size. After that, networking and lightning talks. If any of you is interested in showing any lightning talk you have, reach out to me, Grzegorz, Adam, or Maciej, and just let us know that you want to present. And well, let's start. Now we will switch quickly with Katarzyna, the laptops, and she will start in a moment.
Yeah, I think it looks fine. I hope that everyone sees. And you can hear me well, yeah? Cool. So hello everyone, my name is Katarzyna Kijania, and today I would like to introduce some insights about indoor-outdoor localization. I represent the Łukasiewicz Research Group, Automotive Industry Institute, exactly. And in our institute, we mainly my research group mainly focusing on autonomous platforms, how to adapt them to the just driving in indoor, outdoor, and especially outdoor, but from my perspective, it is more interesting this indoor-outdoor sites. So, short agenda. I will start with defining and determining some challenges in localization with a multi-operational environment. I will discuss what I think, how I defined this multi-operating environment, localization task, classification of localization methods, comparison of selected methods, and then we go through defining the localization reference. I will talk lightly what is localization reference, then research and test, and summary. Few points, but I think we will go quickly. If you have any questions or something get you more interesting, you can ask me, and but I hope that will be some time after presentation too. So, what is the multi-operational environment? In this case, is assumption that the platform functions within diverse external and internal environmental conditions, just in indoor-outdoor area. And as we know, generally, robots has different sensors, and it could be lidars, GNSS, some stereo cameras, or IMU or encoders, and these sensors are always. We put the sensors depending where the robot functions. Where the robot functioning in the outdoor area, then we use probably some GNSSs and IMU, maybe encoders and lidars to make to make the navigation correct. If we go inside, we will could use different sensors. Very often, the outdoor sensors not really good works in the indoor environment. For example, the GPS signal could be lost, and from the different perspective, when we go from the indoor to the outdoor, we can get some camera occlusion and some problems. So, yeah, mainly that. And in the localization task, what is important, I will go through like quickly. I think that some of you may know that because I hope there are some robotic freaks here. And when we talking about localization, we're starting generally from the robot kinematics and wheel rotation. That is classical odometry. And then we need some observations that are provided from the robot perception. Very often it's camera images, lidar scans, and so on. The totally different sensors. And this observation very often make for us some features that when we add some map information, we could combine it. Like here is the map, but it's kind of optional, yeah? So it's not really needed because very often we are trying to build the map basing on this localization task. So from that, we can get the robot position prediction, odometry, as I said, then predicted position after we move, yeah? And when the robot move, we are checking if does it match to the different features that we found in the area. If yes, we have matching observation, then some position update or estimation. It depends what the kind of algorithm we have. Yeah, and that's generally we has this kind of trajectory that is generated. I think I have some laser here. Yeah, lovely. Yeah, so some trajectories, and after that, the loop is closing. Like we're going through this again, and we have current position and next estimations. Very often we are using here sensor fusion to provide the more accurate information about our observations. And when we know the basics, let's say what is localization taxes, how it works, we can go through the classification of localization methods. I made kind of let's say chart, yeah, that based from the sensors, localization types of estimation and fusion, because like the sensors could provide us this observation, localization types defined what kind of localization is it really, and estimation and fusion, that's the kind of method that we are using for this localization. So different kind of sensors that could be provided for the localization types. And yeah, sensors, as you can see, I think that most of them are known. IR is just the infrared radiation detectors. UWB is ultra wideband. It's kind of, let's say, radar, yeah. And when we have some of sensors, we put them very often to the localization types. I put here classification like SLAM. It's simultaneous localization and mapping. I hope that most of you know this name, and it's well known for you. Local localization, when we can just provide only odometry. Global localization, that is map-based. And here I put like satellite. That's the global frame that we have to reference our local frames very often. And some estimation and fusion part, when we can have some filtering, like Kalman filters, probabilistic methods, Monte Carlo localization, NDT, and optimization, factor graphs, Lighting windows, and machine learnings. Yeah, sometimes we are using machine learnings for estimation and fusion, like in localization. I was really shocked because all my life, always people told me that only deterministic methods works. Yeah, and after that, we can just easily combine it. I mean, like using few of the sensors that we have, we can put to the localization type that we would like to just have, like provide to our robot, and we are using estimation and fusion method that could be that just fits in our problem. And what is very important, it's not only horizontally, but also vertically, and we can combine these methods very often together. Like obvious things, we could have IMU lidars in our robots, and we are putting it to the different localization types. Yeah, so it's not like only in one way. Yeah, so. One of the comparison of the selected localization methods that we are going through this all indoor-outdoor environment thing will be the SLAM localization type, where we will be using LiDAR, 3D LiDAR, 3D LiDARs, IMU, and it could be also added some RGB cameras. And after that, we are putting it to the SLAM algorithm, and we will use some probabilistic methods and optimization. I know that it could sound like crazy, like not really understandable sometimes, but trust the process. I will show you just like how to put this together and how to make this localization really works. Because we will use SLAM for the map building, and then we will try to localize our robot on the map based on this probabilistic and optimization methods that we have. And here is some comparison of the selected localization methods. I go through the, let's say, 14th of papers, but there was the most interesting for me from the criteria like high accuracy, tested in the multi-operational environment, sensor ability on the platform, because on our platform that I use for the test, we have IMU, LiDAR, and general cameras. Not really encoders, that is very interesting, but somehow it works based on the engine rotations. And also the one of the most important is to implement, because what if the one method is the best of the all over others, but the most important thing is that it could be really easy to implement. And as you can see from the table, we have here some accuracy also combined, yeah. And here at the bottom you can see what kind of the just this accuracy is. I will not go through the definition of this root mean square error and absolute trajectory error. Just believe me that those of methods are one of the best. Like has the best accuracy and was the easiest to implement for this use case. Few informations about these methods. FastLIO2 method is the LiDAR inertial odometry framework that uses the iterated Kalman filter and dynamic IKD3 data structure to allow for rapid maps updates. Here you have some, GitHub. Just you can check this out. Check this paper on your own. And generally some absolute trajectories errors that was on the previous table, so I will not go really through them. They make some comparison with the others methods. And the second method that I tested was the GLIM method. When we have just 3D SLAM framework that is factor-based graph optimization, and generally they compare some with more methods, also with the FastLIO, yeah, as you can see, and they was one of the best with FastLIO very often, maybe sometimes third best. So generally, what is important, and here is showed that loop closure was used in this GLIM method, and FastLIO method don't really have this loop closure. What is loop closure? Where we are going with our robots, yeah, and we are again through the same area, and the trajectory just crossing again. Loop closure just allow us to correct our current position based on the previous our positioning. Yeah, so it's like very often when you are using SLAM algorithm, you can see that some of them could fix their positions and be have a better trajectory. Yeah. One word about localization reference, because one of the most important thing in researching is ground truth that we have. In this case, in context of localization, this is a trajectory, a set of positions that representing the closest value to the actual trajectory, yeah? Because when we are comparing ourselves, we really would like to just compare with something that is true. We know that from the accuracy of the sensors, yeah? If the sensor is more accurate, that is the best. Here are some examples of this ground truth references. Gauss system LiDARs, some combination of vision and LiDAR IMU sensors, let's say. And one of the most accurate, that is OptiTrack system. We have many cameras that has kind of the ball of the robots, and they could track the position of the robot with 2 millimeters accuracy, so it's really accurate. In these cases, I very often in this research that I will share with you, they has this own ground truth, and it was the simulation ground truth. So it's not really it's not really matter because it was provided in the dataset. Yeah. So one of the research that we made in the simulation environment is comparing the localization methods at the 3D with NDT and ECP. and entity is the nearest distribution transform, and ECP is the iterative closest point. Generally, there are algorithms that provide us that just look on the map, and here we have some vehicle model in the simulation. Then using GLIM, we mapped the area. And then in post-processing, we made kind of the ground truth. And then we just try how this two algorithm works. And what was really interesting, because based on the simulation, we have kind of the two simulational buildings, let's say. One is the driving through a hall, and second one is driving through a warehouse. Yeah. Generally, going with the in the simulation, we simulated the trajectory of the platform, and then just check how this trajectory fits with our ground truth and with the entity and ICP algorithms. And here are some results. We have comparison of driven trajectories for the 3D map. As you can see, ICP was not really so good, and entity was better. I was wondering why. And I think that is the problem of the area that we have mapped, because as you can see, here is the warehouse, 3D map, and here is the whole columns map. As you can see, the whole column has columns. Guess. And there, just the algorithm mess around and put not in this column that it should be. Yeah. Here probably the I'm not really sure but oh, now you can see, I think the area here and here is kind of similar, let's say. So I think that here also algorithm just go not in the correct alley, to the positioning of the map. So after that, when I know that entity is just better from the ICP, I decided to make this our research and test and put this to the in real world environment and check out how it really works. Generally, we compare these two promising algorithms, Leo and GLIM algorithm, to check how this ground through could be used, and which of these algorithms will be better to the ground truth. And for that, we used the Oxford Spire dataset. Has anyone know that dataset? Maybe. Yeah. So generally, it's like really cool data set. I was shocked that something like that is. It's, let's say, kind of new vibe. 2023, 2 years old, 1 year old, something like that. As far as I remember, they're using this geosystems lasers, to make the correct ground truth references. They have sensors and data from the LiDAR IMU, but also from the camera. And here is like the whole structure of this data set. And as you can see, we have some Rosbachs. I think it's not, some poses here, generally poses, but also we have here the Rosbachs. And it's not really something obvious in this kind of data set. I guess that you know Kitty, data set. So in Qt we don't have a really ROS bugs. We can convert them, but here we have everything in one places, and it's cool. What is more is indoor-outdoor environment data set. What was really great information for me, because that's the main, that was that is main research in this cases. Yeah. So one of the scenario here, and this how looks this 3D map of the made with Gleam algorithm. You can see the trajectories and some indoor area here. When we go through this kind of, I don't know, church halls, I have no idea what it really is, but we go from indoor to outdoor, so we have this important transition. And here's some results with this comparison. Ground truth is this ground truth that was provided in Oxford Spire's dataset. In green and in green we have FastLeo 2 algorithm, and in Gleam is on blue. Yeah, and as you can see, Gleam fits almost perfectly in all cases. The trajectory is really nice, but FastLeo 2 goes somehow, somehow, and then in X, because here like we have X dimension, Y and Z, yeah, like the coordinates, and in Z coordinates it through the minus infinity, I guess, or something like that. Yeah, so yeah, here was the starting point, and here starting drive for the activity. So as you can see, this Gleam algorithm was really cool from this perspective of the making the ground through. And trying to answering this question, how to not get lost in the doorway. Yeah, the best method that was I found personally, maybe somebody knows better, is to use just this. Oh, pardon, I have some. Yeah, that will be better. Is just to use some SLAM algorithm like Gleam or FastLeo 2. In our case, it's better to use Gleam because has better accuracy. Then use some local localization to just provide our fitting to the map, yeah, in probabilistic methods like NDT or ICP. And then the best of the best, what could be, will be to provide this global localization to put our map in the global coordinate systems using GNSS or GPS. And in this perspective, we could, for example, put filtering put our information about odometry to Camel filter and provide some matrix that will, let's say, somehow helps us to not really lost in the indoor, yeah, let's say, when we don't have a GPS signal. And you can see at the video, it's not really working system yet, unfortunately. Sorry for saying that. Not really working system for this indoor-outdoor transition, yeah. But here we on our platform we put some just outdoor area system that could navigate from point A to point B, and in next part we'll apply this kind of the systems, yeah, the kind of the algorithm that I show you that I show you. Yeah. Some conclusions. So sensor fusion is really necessary to achieve effective localization and ensure redundancy in a multi-operating environment. Obtain a reliable references value is problematic in the localization task because we don't really have a reference very often, and we need really advanced sensors to provide this kind of references. And errors in localization are usually a combination of the sensor's accuracy, sometimes the methodology, and I think the most important conclusion from that, the GLIM algorithm and NDT method appear to be the best for the robot localization in multi-operating environment, based on the map, of course, because that was the case that we go through. And I think that's all from my side. If you have any questions or you want to talk about that.
So if you have a question, please raise your hand and I'll give you the microphone.
Yeah, so obviously the next question is what comes next? What comes as a next step in this research?
Yeah, thanks for that question. This will be next steps of the research, because right now, as I said, we have the correct working system in the outdoor area, not really in this multi-domain. And probably when we has this kind of tested SLAM methods, which works, and some probabilistic methods that somehow fit our map to the fit our position to the map, then we will try to put this fusion. I think that will be, yeah. Few weeks ago, we provided we collected some rosebugs from this indoor-outdoor area in our institute, and yeah, we will test them.
Okay, thanks. Anybody else? If not, I have another one. Okay. Did you test the case scenario where the robot gets stuck or it goes haywire and, I don't know, runs into something? And then what happens to the mapping algorithm? And do you have like a backup strategy for the SLAM?
You mean like when the robot stucks, yeah?
Yeah, and for example, the wheels spin in place, so the odometry will give the false reading.
I see. Well, not really yet, but in these cases, I think that's the other project that we are doing right now, and it's also interesting. In those cases, I think that the best way is to just monitor the inputs of the sensors, if the value is accurate or not really, and what kind of anomalies we have. And sometimes in this algorithm also, they could be because like we here, like we are mostly uses IMU sensor and LiDAR. So mostly when the robot's stuck, that means it's stuck, yeah. When the problem will start it when the LiDAR or IMU starting to go through the, I don't know, big values, or has some problems, yeah, the sensor itself, or maybe when the we have some, I don't know, reflections or in camera occlusion, as I said here, when we go from the indoor to outdoor, then probably the algorithm should be robust and not really go through that kind of problems. But I don't have an idea how to go through that. Maybe somebody from the... Huh? I didn't understand what you say. The outdoor should be? Robust or... Robust, okay. Yeah.
Do you have more questions?
Hello, thank you. I have a question. Did you consider maybe using some radars for more robust data acquisition here?
Is the could you repeat
okay, sorry. Are you using also radars for like mapping, not only lidars and cameras? For example, to account for the different environmental conditions, and when you go from indoor to outdoor, the lighting conditions change a lot.
Mm-hmm.
So you go from very light to very dark, or from very dark to very light. Yeah. So cameras need to adjust, and if you use radar, then it's like not susceptible to this lighting.
Yeah, exactly. So that's why in these cases we so generally that's why we use the lidars, because it's
radars.
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 I see. Sorry. I found one paper, and I have an honor to meet one researcher from the Austria in Linz, who really did this kind of thing with radars, yeah, and it was really interesting research, but it was one of the not really many. I mean, like they has a robot, yeah, that with implemented radar that go through the area of their campus and make the map, yeah. So and the map was really similar to, you know how it looks the radar map. It's a little bit different than LiDAR, but generally we have also the distance and the parameters are really similar. Yeah, so I found one research, but I do not really test it. From the perspective of the working of in this project, because one of the causes is that our robot do not really has radars. Yeah, so
maybe hard to find that.
Yeah.
Okay, so thanks.
Okay, next.
Maybe I missed this, but what is it was made for? What is the purpose, and maybe some difference?
Okay, yeah, I see. What's the purpose? The idea to make this indoor-outdoor localization, like the whole the concept of the system, was because not only one, but few of our customers has a problem, because very often they using their robots in the indoor area. Sometimes with 6 systems, yeah, so based on 2D lidars with some mirrors, and they don't really, and based on that kind of systems, then they cannot go to the outdoor. So the concept of that was that to make the robot for the able to operate in not only in indoor but also in outdoor. Of course, we can put some kind of hubs that we just putting the things and picking them and then going to the outdoor. But generally, making this this kind of robots able to operate in both of this area. It's interesting case, yeah, and that's why, yeah, to this kind of to make this operation available, and what is the most important, how to make this kind of robots cheap, yeah, and just working here and here, yeah.
Thank you.
Hi, thanks for a great presentation. I'm just curious. I can see on the cost map there are blue borders on the right and left. And based on what data do you detect? Is it like the sidewalk border or?
Yeah, it's the Foxglove, and generally it's like the classic occupancy map.
Yeah, but I'm
so-
curious, like what kind of data you are getting to display this, and is it like really, because I see, far
It's-
away there are also borders of the on the road, like on the right.
Yeah,
and
here,
you,
yeah.
you cannot see it from this perspective. So what kind of data do you use to?
So generally, it's like it was the later data that was put to the dimension. Yeah.
Okay.
So here, where are the borders? Because here is a.
So you did
Pavement?
already map this area before, right?
Yeah,
Okay.
here, yeah,
Okay,
yeah.
I
In
see.
this case, yeah. That's why I told you that here is the map, and the loaded map, and with some drivable area. Yeah, and not really.
And do you think this is the direction for this kind of the problem? I mean, I was thinking about using, OpenStreetMaps. They are quite precise in terms of where the sidewalks and so on. Do you think that could be valuable?
I think for this case, I maybe will show this one, because as I previously said, the idea for this indoor-outdoor research was from the industry. Well, we have where we know where how the warehouses, how the area of the company looks like, yeah, of the hubs. So mainly for this kind of for this kind of area, I think the 3D maps and or 2D maps or wherever really works, because it's not changing a lot. Sometimes somebody put a truck or something different here, but mainly is the same. But when we go through the perspective of the autonomous vehicles, like the classical vehicles, big vehicles, when we have to update these maps and put them together, and just it's like a lot of data, and maybe not really always work. I don't really know. I not think that we have something better. Maybe just GPS signal and current positioning, yeah, and perception, and getting the information from the current perception sensors. But in this case, I think that really could work, yeah, in this indoor-outdoor cases and for the industry.
Thank you very much.
Do we have? Okay.
I'm wondering, how does it adapt when it is not aware of the map? It doesn't have the map, for example. If we are not using a map, how does it adapt to other areas that it is not aware of? The reason why I'm asking is because, an example, those Waymos and Tesla, they have two different approach, where Waymo is using LiDAR, radar, and also the cameras, but Tesla is using only the cameras. They have like, Elon has a way of only saying if a model is good enough, it is gonna be able to even adapt at those new places. But there's problems where it emit with some edge cases where it is unable to adapt, right? And how does it work in your case to solve this kind of problem?
Yeah, thank you for question. I think in my case, in this case, yeah, we focused on multi-sensor and like the sensor fusion, yeah, something that in Tesla very often is not really. Yeah, they decided not to use it, but right now I think that it could be changing in a moment, because we don't really always have the accurate information based only one types of data. Yeah, so here using the multi-sensor fusion and that especially that thing that I showed here. Yeah. Some of the LiDAR, GNSS, IMU, and encoders, and put this all things together, then the information and will be accurate and really met the standards. And I hope that it will be just works. I hope I answered to your
But
question.
without maybe giving it, I can see maybe here you have a map already in place, but what if it doesn't have a map?
If doesn't have a map, well, then probably we could mapping like the continuous, not based on map. So we don't have this part. We don't have the. Yeah, we don't have. Yeah, maybe different. So when we do not have a map, this algorithms allows us to navigate still, like to making our localization not really based on the map. Then we just only use one method, and it's the SLAM method. Yeah, FastLeo2 or GLIM method, and then it will be works. But not really in this. We don't have then the global. Yeah, we have only the local map. Let's say, yeah, that we can combine somehow with the GNS sensors, and maybe and we can go through this this kind of thing, because this two algorithms. I mean, like this. Yeah, this one. And this one, these two algorithms could be work locally, like without the map. Yeah, they are just doing SLAM and they're just mapping.
Even with maybe like in fogs and in different weather conditions.
In fogs.
Different weather conditions, like fog or when it is raining. Or
yeah,
snow.
I think it probably will be works if the conditions are not extreme. Yeah, it probably will be works, because we have a LiDAR and IMU. So if the LiDAR detections, yeah, the LiDAR measurements are okay, that means that it will be works. Yeah. So.
Do we have one more question?
Hello. I have a question. How exactly GNSS helps to when the robot crosses the line between the lack of the signal and the good signal? I mean, the GNSS sensor has about few meters accuracy, so how the mapping can be accurate after the crossing the 2 kilometers warehouse, for example?
It depends, because we can use RTK and then we have 2 centimeters accuracy. Yeah.
Okay.
So mainly independent. Independent. Most of the GNSSs right now, I think, has an option to just put this RTK, and and we don't really need our base station, because there are public base stations that we can also work with. But yeah, it could be really a problem. GNSS very often only is used to put the scanned map, yeah, to the global frame. Yeah, so generally, if we don't have this GNSS, we can just work, let's say, locally or estimate our position. Yeah, previously. Yeah.
Okay, thank you.
One more question, someone?
Yeah, thank you for the great presentation. And as I see, I have lots of questions, so maybe I will just take a short one. From your practice, how often good enough algorithm is, well, good enough for deployment in a real environment?
How often?
How often?
How often? In real environment, yeah?
Yep.
Those two are. I mean, like from my perspective, the most important thing was to just if something is easy to implement, and those two are easy to implement and easy to use. I mean, like very often. Most of the algorithms we can apply it and somehow make it works in the real environment, but it really depends on the researchers and papers. I think if you are talking about this thing or.
I would say that in your research work, when you're taking a new algorithm or you're developing something which seems to be a good enough for you, at least from the research data, if you want to try it on different scenario, and when you are deploying that algorithm, how often is that algorithm works good enough to be said that okay, it could be used in outside the laboratory?
Yeah, so I not have a big such a big that I only working with algorithms and trying to implement them like the I don't have such a big experience, let's say, yeah, but generally those two we implemented and it works, and some different that we tried to wasn't really good enough. For example, the MOLA framework, I tried to use also and implement some algorithms from that. And it was a bit problematic because it works on the ROS bugs, but in the real life, not really, yeah. Yeah.
Alrighty, thank you very much for explanation.
Okay, I see one more question.
Okay.
Thanks. Great presentation, by the way. I don't have one question. I have 3 questions, but I think they will be fast.
Okay.
So my first question, I'm not sure if I should say all of them at the same time or should I go one by one? One by one, maybe, right?
Yeah, maybe yes.
The first question is, from the inputs I saw in the SLAM approach, I didn't see a camera, right? So I'm not sure the goal you have, but without a camera, how can you know? There are things which you need camera for. For example, like reading signs, red lights, stuff like that. How can you?
Generally, we use the camera to just know where the robot is somehow when we try to connect them. But in this approach, I have in plan to test some visual SLAM methods. So then the camera will be used, and it's really helpful. And very often, for example, for those who would like to in the future maybe test some GLIM, they has an option to combine the RGB image on the point cloud. So we have the colorized point cloud. Yeah. So that could be the approach that it could be used.
Okay, nice. Okay, the second question is, how much compute do you need for this SLAM approach? Are you using like something strong as Raspberry Pi? Do you need like a computer?
We tested it on the Vekov computer. It's kind of it's NVIDIA original, I guess, and it works. I'm not measure the exact computing computing parameters.
Okay.
I think they have something in the papers, I hope.
Right. So the last question is, you say that you optimize for the price. So I'm just curious, like, how much cost does it? Like, how much does it cost? Like the hardware for that car.
Oh, okay. So this platform is the bad example of the optimization of the price, but
'Cause it looks expensive. Yeah.
yeah, I mean like the used sensor here is like the research platform. So very often we are just putting the here everything what we can to just try different approaches, but from this price optimization side, I think that the LiDAR and IMU, based only on this LiDAR IMU, let's say 2 sensors, yeah, we could really find something that it's not really cost, in high costs. Right now, I don't know, has anyone of you tried to apply the Livox LiDARs, or you know the Livox? Yeah. so yeah, so you know that it's cheap and it works. Yeah, so very often, and I think that that is a little game changer in this optimization of the price, because those LiDAR are not really expensive, and it could be applied with the IMU, and then we have the working algorithms based only on sensors, yeah.
So maybe removing the encoder and GNS, but what would be the ballpark? Like, how much is it? Like, even if you try to optimize it, like, how much would it be?
How much for the system, let's say, or
the hardware?
Hardware?
Yeah.
Oh, I don't know. I have to check prices of the NVIDIAs and Livoxes and IMUs, but I think that's. I don't know. I don't want to just through the numbers without any coverage.
Okay, thank you.
Okay, I think that's enough questions for today.
Yeah.
So once again, round of applause for Katarzyna.
Thanks.
And we are having a brief change of plans because I managed to reach to Marcin, and apparently his car broke down on the way from Poznań to here. So we have to change a bit plans, and we'll give up on the second presentation, unfortunately. And now we will have about 30 minutes of networking. Beer is over there, so your help for networking is on the table. And afterwards, we'll move on straight to lightning talks. So I think already we have like quite a few of them. And once again, if you're interested, you don't need a presentation. It can even be almost a stand-up vibe. I mean, it's a lightning talk. You have 2 minutes, you have microphone, show something. So have a great networking, and we see each other in 30 minutes.